Hi everyone, these are our notes on exponential and logarithmic functions. For the first part, we are going to look at exponential functions. And an exponential function is defined as f of x equals a to the x power. So with an exponential function, your variable is going to be your exponent. And two things you need to take note of when you're looking at this is a, or the base of the power, must be greater than 0. And it can't be equal to 1. So a has to be greater than 0 and it cannot be equal to 1. And the first thing we're going to do is just evaluate a function. And we're going to evaluate it for f of 3, f of negative 2, f of 0, and f of 2.71 or 2 71/100. So for the first one, remember, what you do is you plug in your value. So I will have f of 3 first, which will be 5 to the third power. And when we evaluate it, 5 to the third power equals 121, or 125, excuse me. Because we did, again, it was 5 times 5 times 5. Next, we have f of negative 2. So that's going to be 5 to the negative second power. And if you recall, when we have a negative exponent, we want to flip it to make the exponent positive. So when we do that, we'll start off, we will have 1 over 5 to the second power. And then we just evaluate it. Our final answer will be 1 over 25. Next, we have f of 0, and when we evaluate it, it would be 5 to the 0 power, and if you recall, anything to the 0 power always equals 1. Our last one is f of 2 71/100. So we'll do 5 to the 2.71 power, and this is one definitely where you want to use a calculator to evaluate it. And we get, I'm going to round my answer to the nearest tenths, so my answer is 78 38/100. So now we're going to graph exponential functions. And we're going to graph them using a table of values and then use our graph to give the domain and range of each function in interval notation. So recall when we graph, we're going to use our t-chart. So I'll make my t-chart with x and y. And then if you recall, y is the same as f of x. And I'm going to pick some x values to substitute into our function. And I'm going to do about 5 of them so we can get a good graph. I'm going to do negative 2, negative 1, 0, 1, and 2. And to find our y values, I'm going to substitute those into our function. So first I will do 3 to the negative second power, which again, remember we want a positive exponent, so we take the reciprocal, and it becomes 1 over 3 to the second, or 1/9. So for our first one, my exponent is 1/9. Next, we have 3 to the negative first power, which is going to become 1 over 3 to the first, or 1/3. Next, we have 3 to the 0 power, and anything to the 0 power equals 1. Then we're going to do 3 to the first power, which is going to equal 3. And our last one, 3 to the second power, is 3 times 3, or 9. So now that we have this, we're going to go ahead and graph our ordered pairs. So first we have negative 2 on the x-axis, and then 1/9, which is really small, so I'm just going to kind of estimate it. That one is going to be hard to put on the graph. Okay, and then we have negative 1 1/3. So again, It's more of an estimate there. If I can get it on there. All right. And then we have 0, 1, so that'll go right here. And then we have 1, 3, so our ordered pair will be right there. And our last one is 2, 9. So it's going to be 2, and then 9 is right here. And then we're going to draw our graph, which I'll try to use blue so you can see it. All right, so when I draw my graph, it's going to go through my points. And then the important thing with this is the graph, when you look at it, it is going to get very close to the y or the x-axis, but it's never going to cross over it and it's never going to touch it. So it's going to ride right along that x-axis, but it will never touch it and it won't cross over it. So we have to do the last thing, which is list the domain and the range. Remember, domain are your x values, range are your y values. For your domain, you want to talk about the x values. We know here that it's going to go all the way through those negatives, and your x values, it's also going to go all the way to the positives, because I can put in any number here on my x side. So my domain is going to be negative infinity to positive infinity. It's all real numbers. So it's going to be negative infinity to positive infinity. Now my range, that's your y-axis. So we're looking here on the y-axis. Our graph for the y values, if you look, will never, because it never crosses over this x-axis, it will never go below 0. It will never be 0. So the range is anything above 0. Let me fix that a little bit. There we go. All right, so my range is anything above 0. So when we write it in integral notation, what we're going to do is we'll put parentheses 0, and the parentheses are because it doesn't include 0, but it can start right after 0, and 0 positive infinity, because it can go, the graph will go up infinitely. So that's our first one. Now for b, we're going to graph g of x equals 1/2 to the x power. So again, I will make my t-chart. And for these, it's the best thing to do is to plug in. We're going to do the -2, -1, 0, 1, and 2. And the first thing I'm going to do is -2. So we'll have g of x, or g of -2, is equal to 1/2 to the -2nd power. And again, to make this into a positive, it's going to end up, we're going to flip our fraction there to give it to a positive value. Or think of it this way, if you want to think of it as one big giant fraction. And when we do the reciprocal, we'll get 1 over 1/2 to the second, which 1/2 to the second power is going to be 1/2 times 1/2, or 1/4. So I have 1 over 1/4, which is really 1 divided by 1/4. And then when we don't divide fractions, we multiply by the reciprocal, so it's going to become 1 times 4 over 1, or equal 4. Next we have 1/2 to the -1st power. And when we do that one, we will get 1 over 1/2, or 1 divided by 1/2, which equals 1 times 2 over 1, or 2. And then I'm going to erase so I have more space. Take a second to do that. Okay, so now we're going to look at the 0 power. So we'll do 1/2 to the 0 power, and anything to the 0 power always equals 1. So we'll put our 1 there. Then we have 1/2 to the first power, which is going to be 1/2. And then we have 1/2 to the second power, which again is 1/2 times 1/2, or it equals 1/4. So now we are ready to graph. And first I have -2, 4, so that will be up here. Put it in red. All right, so it'll be right there. Then we have -1, 2, which is right here. We have 0, 1. And then we have 1, 1/2, which is right there. And then 2, 1/4, which will be a little bit lower. And again, there you're kind of estimating. And then next we're going to draw our curve that we have. And again, it's going to go not up like that, but right along that x-axis. It will never touch the x-axis, and it will never cross over the x-axis, but it'll ride right along the x-axis. Now, when we look at our domain and range, it's going to be the same as the last problem, because if you look at our x values, this graph will always go up and out. So we'll have negative x values and positive x values. So my domain is going to be -infinity to +infinity. And my range, again, will be, it can't ever be 0, but it'll be anything above the 0. So we'll put a parenthesis, 0, comma, +infinity. And again, that parenthesis stands for, like if we were graphing, that it doesn't include 0, but it starts right after it. So I could use 0.01, 0.02, something like that, but I can't use 0. So the parenthesis says it starts right after 0, but it doesn't include it. All right, now we have our final example here with the graphing. This time we have h of x equals 2 to the -x power. So again, I'm going to make my t-chart, and I'll have my x and my y. And I'm going to plug in -2, -1, 0, 1, and 2. And my first value is -2, so I will do 2, and it's -x, so it's going to be negative, and then I'll put my -2 in there. So really, if you think about it, that double negative up there, because they made it the opposite of x here, or that -x, it's going to turn it into a +2, because really think of it like this, it's like a -1 on the outside, so -1 times -2 will give me 2 to the second power, and it equals 4. Next, we'll do 2 to the -first power, and again, because it is 2, we have that opposite of x there, it'll be that negative on the outside, and your -1, which the two negatives make it into a positive, so we will have 2 to the first power, or 2. Then we have 2 to the 0 power, and even though it's negative, 0 is not positive or negative, so it's still going to be 1. Then we'll have 2, and we'll have our negative on the outside to the first power. Because we only have that one negative, it's going to end up being 2 to the -first power, or 1/2. And then last, we'll have 2 to the opposite of 2, or -2, so it's going to be 1 over 2 to the second, or 1/4. And then we'll go ahead and graph that. So we have -2 to the 4th, which will be right here, -1 to the second, 0, 1, 1, 1/2, so it'll be right around there. Make it a little bit bigger there. And then 2, 1/4, which will be right here. If I can get it to right. All right, and then we draw our graph. Again, it goes right along that x-axis, but never touches it. Now, again, if you look at it, our domain and range is going to be the same as the last two problems. The domain is going to be negative infinity to positive infinity, because you can have any value for x, for the exponent. And the range, again, it's not going to go below that 0 on the y-axis. So we're going to have 0, comma, infinity. And we'll put parentheses around all of that. Now, D says comments on the graphs in parts B and C. If you look at the two graphs, if you compare them, they are exactly the same, because 1/2 to the x power is the same as 2 to the negative x power. Now we're going to look at logarithmic expressions, and we're going to take our logarithmic expressions first and write them as exponential expressions. Now, a logarithmic function is the inverse of an exponential function. So again, you think you're switching your x and your y's. Your log or logarithm is defined as y equals log b, which will be a subscript down there, of x. If and only if x is equal to b to the y power. And think, this is it as a power. You have x and y switched. B is your base. So here, our requirements are x has to be greater than 0, and y has to be a real number. And again, remember with inverse functions, you switch your x and your y. So what they did with the log is they switched the x and the y. So what we're going to do for the first one is we're going to take our log and write it as an exponential function. Now, when you look at this problem, the little number here, this always tells you the base. So that's going to become our big number. So we're going to have 5. And then the answer here, or the big number, or the number after the log, this is your x and this is your y. So remember, it is log b to the x equals y. So when we put it in exponential form, we will rewrite everything as a power. So I'm going to erase the 5 and move it down a little bit. All right, so our little number on our log is our base to our exponent, so we have 5. Then this becomes our answer. So it equals x, or it equals 125. And the answer on the log, that's our y, that's our exponent. So, and if you look at it, it makes sense. We have 5 to the third power equals 125. For the second one, we have log 1/8 of 2 is equal to 1/3, or negative 3. So again, we're going to start off, 2 will be our base. And then my exponent is the answer. So we have 2 to the negative third power, and it equals the number with the base, 1/8. And then our last one here, 9 will be our base. Our exponent is the answer, so it'll be 9 to the 3/2 power. Oops, let me fix that. Is equal to 27, or this part right here. All right, so now we're going to take 3 examples, and they're in exponential form. We're going to put them in log form. So just as a reminder, we have y equals log b of x, and that is the same as x equals b of y. So this is the log form, this is exponential form. So if we have exponential form and we want to put it in logarithmic form, what we're going to do is, remember your y is your exponent. So here's my y value, that's my exponent. The base of your exponent, or your power, is your b, and the answer is your x. So I will have, in this case, 5 equals log 2 of 32. We'll do the same thing with the next one. We will have log 64 of, remember your answer, this is your x, 16 is equal to, it's equal to your exponent. So this is your y, so it's equal to 2/3. And then our last one will be log, we'll put our 81 down below, of 1/9 is equal to -1/2. And that's it. So here what we need to do is they want us to evaluate each logarithmic expression or find out what it equals. So to do this, we're going to put it into exponential form because I think it's easier to see. And remember, our logs equal y. So we have log 2 of 16, and we're going to take it, we're going to do, what you're going to do is, our exponential form would be 2 to the y power equals 16. So basically what we're finding out is what is the exponent that would give us 16. And in that case, it would be 4. So y equals 4, because 2 to the 4th power gives us 16. And for these, like the ones we do, they'll be your perfect squares or cubes. So really use like trial and error to kind of find them. Our next one, we will have 10 to the y power equals 1,000. And I know that 10 to the 2nd power equals 100, and 10 to the 3rd power equals 1,000. So y is going to be 3. So we will, like up here, we can write it equals 3 for our final answer. And up here, instead of equals y, we'll put equals 4. Our next one, because it is a fraction, we're going to have 3 to the y power equals 127. Here's what I want you to remember. When you have a negative exponent, that's when you do the reciprocal and you end up with that fraction for an answer. So think of it this way. 3 to the what power gives us 27? And I know 3 to the 2nd is 9. 3 to the 3rd equals 27. But I need 127, so our answer is going to be a -3, because 3 to the -3rd power will give us 1 over 27. All right, next we have 6 to the y power is equal to 1/36. So again, we have a fraction for our answer. So think negative exponents when you have that fraction there. And I know that 6 to the 2nd power equals 36, so my answer is going to be a -2, because that will give us -2 will give us 1/36 for our answer. Next, we're going to have to think radicals a little bit. So we're going to have 9 to the y power equals 3. And this is where you have to think, remember with your fractions, and I'll tell you this one is 9 to the 1/2 power equals 3. If your answer is smaller than your original number or your base, think fractions, think radicals. Because remember, if you have 9 to the 1/2 power, they're really looking at the square root of 9, and that's going to be 3. So our answer here is 1/2. And then here we have 8 to the y power equals 2. So you're taking 8 and making it smaller, so we're really going to look at like a square root or a cubed root or a radical here. And I happen to know that 2 to the 3rd power gives me 8, but I want to go the other way. So we're going to look at the cubed root of 8, which if we write it as a fraction, remember, is 8 to the 1/3 power. So our answer here for y is 1/3. So here we are graphing logarithmic functions. And in order to graph a logarithmic function, the first thing you want to do is put it into exponential form. So remember, our log 2 of x would be written as 2 to the y power equals x. And again, remember, a log is the inverse of a function, so the x and the y are switched. So if you noticed on our t-chart, they gave us y values, we have to find the x. So we'll start off with 2 to the -2nd power, which again, remember, you do the reciprocal. So it's 1 over 2 to the 2nd, or 1/4. Then we have 2 to the -1st power, which is going to be 1 over 2 to the 1st, or 1/2. 2 to the 0 power is always going to be equal to 1. 2 to the 1st power always equals 2, and 2 to the 2nd will give us 4. All right, now that we found our t-chart, we're going to go ahead and graph. So first we have 1/4 -2, and again, for that one, it'll kind of be an estimate. 1/2 -1, so right around there. 1, 0 will be here. 2, 1 is right there, and 4, 2 will be right there. And then we'll draw the graph. And again, just like before, it'll go right along an axis but not touch it. In this case, it's the inverse. So if you notice our graph, this time it goes right along the y-axis but never touches it. So your domain and range for a log function will be reversed. Your domain will be from 0 to positive infinity, and your range will be negative infinity to positive infinity. Right here we're going to graph log 3 of x. So again, when we write it in exponential form, it would be 3 to the y power equals x. And we'll go ahead and plug in our y values. So we'll have 3 to the -2nd power, which again, we'll do the reciprocal. So it'll be 1 over 3 to the 2nd, or 1/9. Then we'll have 3 to the -1st power, which will equal 1 over 3. So we'll have 1/3. Anything to the 0 power equals 1. 3 to the 1st power equals 3. And 3 to the 2nd power equals 9. And we'll go ahead and graph it. And again, the 1/9 and the 1/3, you're going to really have to estimate those on the t-chart. So 1/9 -2 will be somewhere right in there. 1/3 -1 will be right about there. 0, 1 is right there. 3, 1, and then 9, 2. And then we'll draw our line. And there's our graph. And again, the domain and range is opposite of an exponential function, so our domain is 0 to infinity, and our range is negative infinity to infinity. So now we're looking at our applications of exponential functions. We're going to start with compound interest. So the first thing we're going to do is we have an equation where the amount that you'll have in the end is equal to the principal, or the amount that you put into the account, the initial investment, times 1 plus your rate, which should be written as a decimal, divided by the number of times compounded, and this is all raised to the nt power, or the number of times compounded by the length of the investment in years. So we're going to start off here with $1,000, and it's compounded quarterly. So quarterly is the number of times per year. Quarterly is always 4. Think of 4 quarters in a dollar, 4 quarters in a year. At 3.1% interest, and it is left in the account for 6 years. We want to approximate the amount after 6 years. So we'll start off with our A equals, our principal amount is the amount that Jenny put in, which was 1,000, times 1 plus, now our rate is 3.1%, but we need that as a decimal. So remember, move it over 2 places. So you have decimal point 031 over n, the number of times compounded, which is 4. And then it's going to be raised to the nt power, which is 4, and then 6 years, so 6. When we do the math, remember, parentheses first. So I'm going to start and divide my 0.031 by 4, and then add 1, and that will give me 1.00775. And the important thing here is don't round until the very end. So keep that long decimal that you get on your calculator. And then 4 times 6 I'm going to do is 24. So next I'm going to raise this to the 24th power, which will give me 1,000 times 1.203558942. And when we multiply by 1,000, this final step is where we'll round. The more you round in the beginning, the less likely your answer will be, or the more off your answer will be, and the less likely you'll get all your money. So you definitely only want to round at the end. And our final answer, when I round it, is $1,203.56. Okay, so now we're going to compare a $20,000 investment for 3 years to an account that's compounded monthly, which, if it's monthly, it's 12 times a month, or daily, which would be 365 days per year. So when we do our calculations for the first one, we'll have our 20,000 times 1 plus, again, we'll do our rate, which is 2% for the first one, so 0.02, and it's compounded monthly, so it'll be over 12. And then our exponent will be 12, which is our number of times compounded, times the number of years, which is 3. So when we do the math on the inside, we'll get 20,000 times 1.001, and then 66667. Again, my calculator just rounded it. It was 0.6 repeating, or the 6 was repeating. And then 12 times 3 is 36. So then we'll raise this to the 36th power, because it's this times this, and then we do multiplication last. So we're going to have 20,000 times 1.061783515. And when we do our final multiplication, we get $21,235.67. Next, for compounded daily, we're going to do 20,000 times 1 plus, my interest rate here is 1.5%, so it'll be 0.015 over 365, and then our exponent will be 365 times 3 years. So then we'll do the inside first, and we get 1.000041096, and 365 times 3 is 1,095. So when we raise this to our exponent, we'll get 20,000 times 1.046026893, and then when we multiply, we get $20,920.54. So the higher interest rate is better, even though it was only compounded monthly. We got 21,000 compared to our 20,000 here. Okay, so here we are looking at the amounts of growth that a fruit fly population has, exponential growth, and our formula is our initial amount times 1 plus the rate of growth raised to the length of the growth. And we have fruit flies that initially start at 100, and they grow at a rate of 2% per hour. And the important thing here is this is per hours. So when we do our formula, we have to use hours for all of our formulas. So this one's okay, we have 6 hours. Days, we need to convert to hours. So I'll do 5 times 24, which gives me 120 hours. And then 75 divided by 60 will give me 1¼ hours, 1.25 hours. And we're just going to plug them into our formula now. So for the first one, we'll do 100 times 1 plus my rate, which we'll write as a decimal, so 0.02 raised to the 6th power. So we have 100 times 1.02 to the 6th power, which is 100 times, and again, don't round until the very end, so it'll be 1.1262419, which when I multiply by 100 is 112 and 62 hundredths about, but we're talking fruit flies, so we're going to round it to 113. Next, we'll do 100 times 1.02. I'm just going to go ahead and add it to the 120th power. So we get 100 times 10.76516303, which is the same as 1,076 and 52 hundredths. But again, we're talking about fruit flies, so we're going to estimate it at 1,077. And then our last one will be 100 times 1 and 200 raised to the 1.25 power, which is going to give me 100 times 1.025062219, and that's going to equal 102 and 51 hundredths, or about 103 fruit flies. Okay, now for our last example, we're going to look at the value of a car and how much it depreciates per year. So again, our formula for our time is our length of decay. It decays by 15% each year, so our time always has to be in years. The first one, I have 10 years, we're good. The second one, I'm going to take 30, divide it by 12, which are 12 months in a year, and it will give me 2.5 years. And that's what we'll use for our time. So we're going to start off, we had a $25,000 car. That was our initial amount And then it's going to be 1 minus our depreciation, which is 15%, so 0.15. And then we'll raise it to the first one, 10 years. So when I do the subtraction, I get 25,000 times 85 hundredths raised to the power of 10, which gives me 25,000 times 0.1968744,043. And after 10 years, the car is worth approximately $4,921.86. And then the last one, 25,000 times 1 minus the 15 hundredths raised to the 2.5 power. So we'll have 25,000 times 0.85 raised to the 2.5 power. So we'll do 25,000 times, when I do my power to this, I'm going to get 0.666112087. And that's going to give me, after 2.5 years, the car is worth $16,652.80. That's it for now. The last example on half-lives we're going to skip. We're not going to, you're not tested on it. You're not going to be worried about it. So we're going to stop here with the notes.